Hello everyone, let's talk about the lens formula. So lens formula for spherical lenses is a relationship between the focal length, the image distance and object distance of the spherical lens, and it is given by this 1 upon v minus 1 upon u equals to 1 upon f, where v is the image distance, u is the object distance and this is the focal length of the spherical lens. Now let's talk about the linear magnification for spherical lenses. Linear magnification, represented by small m, is defined as the ratio of the height of the image that is formed after refraction to the to the height of the object. So it is also equal to v upon u in case of spherical lenses. Now we have seen that in concave lens, since the size of the image formed is always less than the size of the object, that is h dash for concave lenses is always going to be less than the height of the object h. So the value of magnification for concave lenses in every case is going to be less than 1. Whereas in case of convex lens, we saw that convex lens forms all the types of images. So if the height of the image is equal to that of the height of the object, the value of m is going to be 1. If the height of the image formed by the convex lens after refraction is greater than that of the object, the value of m is going to be greater than 1. If the image formed is lesser or smaller than the object, m is going to be less than 1 for convex lenses. Now, since concave lenses always form virtual images, that is, the image formed is always on the positive y-axis, that implies that h dash for concave lenses is always positive. So the value of magnification for concave lenses is also going to be positive. Whereas in case of convex lens, if the image is virtual, then h dash will be positive and m will be also positive. But if the image formed by the convex lens is real, then the h dash is going to be negative, since the real image is going to be formed on the negative y-axis, and in this case m will also be negative. So for virtual images, the value of magnification is positive, whereas it is negative for the real images formed by the convex lens. And for concave lenses, m is always going to be positive. Now let's see the power of the lens. Whenever a concave lens diverges the light or a convex lens converges the light rays, so this ability of converging and diverging of the light rays by the respective lenses is known as the power of the lens, and it is expressed as the reciprocal of the focal length of the lens. That means the converging or the diverging ability of both the lenses directly depends on the focal length of the lens. Talking about the SI unit of power of the lens, so the SI unit of power of the lens is diopter. And one diopter is expressed as the power of the lens whose focal length is equals to 1 meters. So when the power of the lens is expressed in meters, this is the standard case. 1 diopter equals to 1 meter inverse. Now since we know that a convex lens is a converging lens whose focal length is always positive, so the power of the convex lens is always expressed in positive. Whereas concave lens, being the diverging lens, its focal length is negative, so the power of concave lens is expressed in the negative as well. Let us talk about the combination of lenses. Suppose if these lenses are placed in a combination with each other, then in that case, what is going to be the power of this combination of lens? Let's study. It's very simple. The net power of this combination of lens is going to be equal to the algebraic sum of the individual powers. For example, this is a convex lens, a converging lens. So its power is going to be positive. Let us say plus 3 diopter. This is again a convex lens. Let us say its power is plus 4 diopter. This is a concave lens, diverging lens. Power will be expressed in minus. Let us say its power is minus 2 diopters. Then the net power of this combination of lens is going to be plus 3 plus 4 plus minus 2. That is 5 diopters. So this was the concept of combination of the lenses.